The nature of soil. What is soil? Soil is the medium of life, and from which all life springs, maintains itself, and returns. It, like water and air, is a critical natural resource. Soil is comprised of both living and non-living elements that together provide the basis for maintaining life on this planet. We are made of soil, as is all organic life, plants, animals, microbes, fungi, and bacteria. We can look at soil through at least 5 major lenses: soil chemistry, soil biology, soil agronomy, soil biophysics, and soil history. They are all interrelated, but traditionally were separated branches of study. Because of this, we've overlooked some incredible things. A new picture is emerging that isn't one or the other, but everything stacked and interacting in real time. It's a symphony of life that is humbling when we are able to witness its rhythms and patterns. There's life of all sorts at work constantly, but the medium through which it all travels itself is cousin to the semiconductor, as we will learn further on in this book. Soil redox is, after all, measured in millivolts. Soil is many things at once. It is mineral, chemical, water, air, biology, habitat, and a living system of mineral and biological electrical currents. It is easiest to think of the soil in groups as most scientists do, but with a new twist: mineral, organic matter, humic, and biological. But by separating them into disciplines of study, we've missed how they work together fundamentally. Organic matter for years has been overlooked, underrated, or a mystery to most scientists. Even today, there is debate as to what humic compounds or humus really is. Its critical role, and the soil food webs as well, need to be conveyed in tandem with soil chemistry and mineral profiles. It is powerful to see them all working together as seamlessly as you operating your computer. And this works well as a guiding metaphor because silicon computer chips are cousins to clay, sand, and silt, which are all different fraction sizes of silicon compounds. Silicates are the largest mineral group in the Earth's crust. It's no wonder that nutrients and electrons are conducted and attracted through the soil profile when we see the soil as comprised of silicates of varying sizes and varying paramagnetism, augmented and infused with a program of humic compounds of a great diversity of sizes and arrangements with which the operators, the soil food web, can use to activate and animate the soil. Everything is infused. The humic compounds are connected to the minerals are contained in the humus in biology, including us. So keep that in mind. This is a useful metaphor, but all metaphors have limits in science especially. Rely upon them to generate fluency, but not static thought. Always be ready to adapt your thinking. The soil is truly alien territory for us giants, and we need to remember that and keep it in mind. There is a visual for this here on this page that everyone should check out. If you just go online, you'll be able to see this. You can download this in the ebook, or this is in your physical book. But look at this and think about this. Download this. The hardware. The parent materials, the clay, sand, silt, rocks, and pebbles. All these are the mineral hardware that the internet of the soil runs on. Clay, sand, and silt are all silicate fractions of very different sizes, and so they have different behaviors in the soil environment. They are in essence the microprocessors of the microbiological world of soil. In many ways, they cannot be changed quickly or dramatically. A low CEC, cation exchange capacity soil, is baked in to an extent. Think of the CEC as your processor speed and the memory capacity combined. Think of the parent materials as the brand of the hardware, since it largely determines the CEC and mineral profile. We could ship in clay or sand to alter the hardware, but for most of the world, this is unrealistic. The caveat would be that adding biochar, rock dust, and other mineral amendments, especially paramagnetic ones, would be like adding a hardware enhancement, like installing more memory into a computer, which in the recent past was easy to do. It wouldn't fundamentally alter the hardware, but would enhance it in specific ways. The software. There are so many different types of organic matter, and each type lends itself to a different program, a different ecosystemic direction, different cycle and succession. Organic matter in the form of humic compounds expands CEC, holds more water, and provides the habitat, food, and setting for all life to survive and thrive in the soil. It also directly relates to EH, soil redox levels, and organic matter serves as the battery for the energy in the soil. Without it, plants are short-lived, stunted, and barren. All organic life decomposes into organic matter, some of which is turned into humus. We might consider the long-term stable humic compounds, the humus, to be the operating system, the OS, like Windows, Linux, or Mac, and the more ephemeral and transitory organic matter to be like programs and apps. You may only use that computer a certain time of the year, like a program designed to help you with your annual taxes, or like a winter cover crop, but it is important, has a short window of time for completion, and has lasting effects. The operators. For some time, observant farmers have known that organic matter and living soils were key to healthy plants, but we now have the long-term evidence that we cannot manage the soil without the soil food web members, plants, and soil organic matter. By relying upon the soil food web and plants as the expert programmers and managers of our soil, we can accomplish things once thought to be impossible in the agrochemical world. If we work through them, we can accomplish long-term regenerative growth, improving profits while building soil and growing beyond organic food. What happens when the tech illiterate boss tries to program the new software himself? Nothing good. He may know the objectives, he may even know some of the concepts at work, and he's seen the start and the finish before, but he doesn't know the context, the seasons and cycles, the details and the math that goes into it. In the past, we've done this very thing and then run soils and ecosystems into the ground. Today, we are still doing it, but at least we are somewhat aware, trying to figure out how to stop it. This book is to help you avoid the mistakes of the past and to introduce you to the powerful partnerships with the natural architects, engineers, and hands-on workers who live and die in the rhizosphere. They are the experts, the real bulwark of change, and the linchpins to all living systems. Without them, it would be all just dead dirt, and plants and animals would not be able to survive. Just remember this simple metaphor as we delve into the depths of soil science. It can get overwhelming at times, so just remember that we need an operational computer, a complete OS, and a team of experts to have optimal soil performance. And we can achieve this easily if we just test our soils, identify the problem areas, select the solutions that work for us from this manual, and apply them. The power. Now, it may go without saying, but I'm saying it all the same. The sun is the power in reality and in this metaphor. It provides the charge for the entire system to run. The plants are the solar panels that bring carbon, energy, and protons into the soil profile and reducing the soil. Adding electrons, in other words, charging it while making it more acidic. Photosynthetic energy is stored in the organic matter. It's the battery. But without the sun, we cannot charge it. This is why photosynthesis is so important. Without it, we cannot have healthy living soils. Paraphrasing Oliver Hewson, we can grow plants without soil, albeit unhealthily, but we cannot grow soil without plants. And we'll add one more extension to this. We cannot grow soil without photosynthesis. The origins of natural soils. We didn't start out with rich loam soil. It's taken billions of years to get to where we are now. Over time, the primary processes driving soil erosion, creation, and fertility have been added to. Initially, the world didn't have soils as we know them. They didn't have living components in them to perform the soil cycles. Instead, it was physical and chemical changes that initially drove the creation of primordial, purely mineral soils. In the newly created substrate, fungi, bacteria, archaea, and then later early microscopic animals and plants added their own physical and chemical methods to break down, enrich, and create more soil in more ways and at a faster pace. All this activity generated the organic matter components of soils we have today. As microbiology has adapted and evolved over time, so has the macro world. Fungi formed the first tree-like structures before trees even appeared, and it is arguable that all trees, plants, and animals are also fungi. At one point, before white and brown rot fungus had developed, trees grew and began to dominate the landscape, only to die and fail to decompose over time, piling up all over the land, leading to massive fires until fungi began its work. Without the soil biology, we would not be able to create soil quickly today, or have it serve in so many amazing ways. Rich soil can hold enormous amounts of water on land, and in just a small fraction of soil, billions of microscopic beings exist. If there was no water and no organic matter, there would be no significant life there. Life serves to cycle the nutrition in the soil food web in service of themselves and plants, the backbones of the macro ecosystem. All the animals rely upon the plants, even the carnivores, since they eat the herbivores. In this way, we can see that evolution began with the soil, then plants, then animals. Because we can recreate this succession today on sites all over the world damaged by agriculture, mining, and other destructive human activities. We can recreate the processes and history of the world on our homestead or even in our bioregion and recreate our very own Edenic paradise. But it always starts with the soil. So let's look at the history of soil a bit deeper to uncover what matters to us and can help us now. Soil can be created through pressure, friction, impact, or other physical actions to separate molecular structures of the rock, the parent material that will become soil. Soil is being created and eroded all the time every day. Right now, glaciers are grinding against rock, making a fine mineral silt that is being carried away by the water from the melting ice. Right now, natural erosion is carrying away topsoil from forests, peaks, and riverbanks. Volcanoes erupt and lava forms new rock regularly as well. It's a constant process if you're looking at the Earth at a global macro level. It also happens quicker than we realize. For a long time, we thought soil took thousands upon thousands of years to grow. Not so. We can create soil quickly if we understand how to partner with microbiology effectively. And it's easier than it sounds. Even a child can create soil safely. But understanding soil and creating the kind of soil that aligns with your goals is very different. We need to know the parent materials, their elements, their influence, and to understand all the minerals and their roles. Only then will the behaviors of the soil food web and plants make sense. Quote, soil is a function of parent material, climate, living organisms, topography, and time. End quote. Hans Jenny, 1941. Clay. Clay, sand, and silt are actually fraction sizes of rock. They also let us know the surface area and thus capacity to hold nutrients in the soil, the CEC. Clays are the smallest fraction size of soil particle and in many ways the most useful. High clay soils have a higher surface area, carry a net negative charge, and can hold more nutrients and water. Though heavy clay soils take this holding capacity to the extreme and can even be hydrophobic at a certain threshold. Clays hold minerals that plant roots trade for with H+ ions, with hydrogen ions, with protons. Clays are made over long spans of time through chemical weathering and hydrothermal processes, primarily through carbonic acids formed by rains passing through the topsoils. They are primarily formed from silicate-bearing parent materials and are found in place of their creation as well as transported by weather and other natural phenomena. Clays often have concentrations of quartz, metal oxides, and even water trapped in them. A unique molecular structure makes clay sticky, malleable, and a great building material. It is theorized that all cellular life began on the edges of clay particles that conduct electrons and attract the building blocks for cells, nucleotides, and even link them into chains. Elements in clay. Silicate materials, often with metal oxides, quartz, trace metals, and non-metal minerals, and water. Because of clay's superior CEC, it tends to always have a variety of nutrients bound in its structure, especially water. Examples of these are kaolinite, known as kaolin clay to many organic orchardists, palygurskite, a magnesium aluminum phyllosilicate common in the American Southwest, vermiculite, and many more. Silt. Silts are fine grains of soil, but much larger than clays. They are primarily fractions of quartz and feldspar, and while larger than clay, they can be much more mobile. Silty soils can erode easily and even blow or wash away if not managed properly. Most silty soils are found with some clay and sand, but some areas, especially riverbeds and floodplains, are dominated by silt, which can be very rich in nutrients. The fertility of the Loess Plateau, the Fertile Crescent, and the Egyptian Nile floodplains was all centered around the mobility and richness of silt. Every year the floods would replenish the fields with new silt until overexploitation degraded the system too far to recover, or in the case of the Nile, until the British dammed it and ended the annual flooding. Silts are created through physical processes: glacial, fluvial, water movement, aeolian, wind, and chemical processes like haloclasty, where salts form in interstitial spaces and expand in heat, fragmenting the rock and leaving salt deposits in their wake. Elements in silt. While sand is often composed of the most two common elements in the crust, silt is composed of the two most common minerals, i.e. solid chemical compounds, in the continental Earth's crusts. They are feldspars and quartz. Sand. Sand is larger than silt. You can see a grain of sand easily with the naked eye or with your glasses on. The majority of sand on Earth is made of silica and oxygen, primarily derived from quartz, but in tropical areas where coral reefs and shellfish thrive, the sands are made of calcium carbonate. Sand, like clay, is a powerful building material, but it is also a non-renewable resource, as concrete manufacturers source desirable beach sands rather than desert sands, which are unsuitable for construction. Sandy soils also have low CEC, so it is difficult for them to hold nutrients and minerals. They tend to wash out with the rain or irrigation. Elements in sand. Silicon and oxygen. Silicon is the second most abundant element in Earth's crust, and oxygen is the first. Because sand has low CEC, it does not carry many trace minerals or nutrients. Organic matter. Organic matter is sometimes not even considered as an important component of the soil because it is such a small fraction of the topsoil. This wasn't always true. At one time, the traditional agricultural soils all had much higher levels of organic matter. That's why we initially were drawn to them. Let me show you what I mean. Close your eyes and imagine good soil. What do you see? Was it dark in color? Did it have crumb structure? The color primarily comes from the organic matter. The black comes specifically from carbon molecules. The structure comes from fungi and bacteria. If you take a jar of soil and water and shake it up, you lose that structure. Organic matter floats to the top, and you can even see the color separate. Without organic matter in soil life, soils wouldn't be able to generate, support, and recycle life. Sand, clay, and silt are non-living, mineral-based substances and do not have the necessary components to support, create, or decompose living organisms. There are chemical and physical processes at work and implicit in the geomorphological history of all soils and bioregions, but the cycles of the soil beyond these processes are all biological and often require organic matter to be present, though lichens and other organisms can generate and or capture organic matter as well. If we want healthy, rich soils, we need both organic matter and a diversity of soil life to maintain and direct the cycles of the soil. Quote, for every 1% increase in carbon to 30 centimeters, we increase the water holding capacity of soil by 166,000 liters per hectare on every rainfall event. It's from Colin Seiss in the movie 2040. Organic matter is also the key to building soils. Unless you are trucking in sand, silt, or clay to literally change the composition of the naturally occurring soil, you are only going to increase topsoil depth and loam structure through adding organic matter and working with soil biology. You may add in specific minerals, amendments, and other small additions to the soil, but all the essential elements for plants are found in healthy plant residues. The CEC of all soil types rises in correlation with raised organic matter levels, and the soil food web depends on organic matter for nutrition and habitat. Organic matter is also the reservoir of electrons in the soil. Soil organic matter both buffers the pH towards neutral, slightly acidic, and increases EH poise. Organic matter shifts both to an ideal state for growing healthy and nutritious food and supporting the most beneficial soil life. In a very real way, organic matter is like the operating system that brings the inert sand, silt, clay, rocks, and pebbles into function, just like our computer is blank without its OS. The soil's OS is organic matter. Soil's OS is OM. It makes the hardware functional, but it needs biology to operate it. It's a complex OS that has ancient experts, the soil food web, that have been guiding it and using it to drive the succession of life and all biodiversity. While humans have attempted to directly influence and direct soils using specific synthetic nutrients, NPK, and machines, the past 100 years or so of agriculture have largely been missing the importance of OM, organic matter, even as their systems have relied upon it. Synthetic nitrogen solubilizes soil organic matter, and their systems and synthetic inputs have killed the biology in topsoil at the same time. To be specific, the synthetic nitrogen solubilizes the humus, soil organic matter, along with all its nutrition so plants rapidly absorb the nutrients. But the trade-off is the rest is leached away, and humus takes a long time to develop, so they quickly erode the soils and they wash away. So what is organic matter exactly? All organic molecules contain carbon, hydrogen, nitrogen, and oxygen. Our most fundamental constituents are just water, carbon, and nitrogen. Humans really are just earth, air, and water combined. Air. While it might seem obvious, having interstitial spaces or pores in the soil is vital to all aerobic soil life. The soil itself breathes in a way. Diffusion is constantly happening, and soil life is producing and consuming gases all the time. While it ranges, healthy soils are mostly just air. 80 to 90% of organic soils are just pore space. Isn't that wild? The same principle holds for atoms. There's mostly empty space inside them. Water. Water is so ubiquitous and quixotic that it is almost always overlooked and taken for granted. It is still baffling and intriguing today, as it has always been to those that observe it closely. Almost everyone knows the textbook, public school, and university definitions of water, liquid, vapor, and frozen, but there are gel and easy water states, which are found all around us all the time. And things get really wild under pressure, where we find diamondized water in the deepest boreholes of the earth. Which really begs the question, what is our world made of? We have surmised for so long that we assume it's an iron nickel dynamo core with magma encircling it, but we don't really know. The fact that there is water, where we imagined magma, water in a new state, and filled with microscopic life at the greatest depths we can reach, suggests our planet is deeply seeded with life and water. We can also assume that we are not done learning about water and its mysterious nature. Water in soils is vital. Most folks know you need sufficient water to grow a garden or orchard, but it depends a lot on the crop and your focus. Avocados require 74 gallons of water to produce just 1 pound of fruit in the regions of California where they can be grown. It's also what kind of water do you have? Is it hard or soft water? If it's too hard, the carbonates and bicarbonates in the water will bind with the nutrients and minerals in the soil, compost, fertilizer, microbial inoculant, and reduce efficacy by up to 70%. But just using a reverse osmosis water filtration system can reduce application rates by 30 to 50%. 80% of U.S. farmers using well water have hard water. Ideally, water should have less than 70 parts per million total hardness, but that is hard to come by. So most will require an RO filtration system. According to John Kemp, the non-RO filtered water, softened water, pond or stream water, city water, and chemically acidified waters are all unsuitable for making foliar sprays. They contain too many minerals that are harmful to biology and counteractive to a majority of the effect. Easy water. Exclusion zone, easy, water forms a lattice of H3O2 that forms the crystalline structure of colloids, which are vital to soil structure, function, and remediation. It creates a polarity of charge, negative on the surface and positive just outside. Though only in recent years identified by Dr. Gerald Pollack, we can see it everywhere. This is how clouds form. water droplets dance across the surface of water, and electricity gets conducted into form in the soil. The exclusion zone is also charged and expanded by sunlight, specifically by infrared light, i.e., water structure, form, and behavior are dramatically affected by sunlight. Water absorbs the radiant energy from the sun like a solar panel battery and even polarizes into predictable negative and positive regions. Inside our cells, easy water too takes on charge from the sun, develops charge separation, and provides energy to the cell. This is similar to photosynthesis for plants, but happens in animal cells. Easy water, the fourth phase of water, is structured water, often experienced as a gel or an area of exclusion around hydrophilic substances. It is found on all hydrophilic surfaces in our bodies, in the bodies of all animals, and in plants. The unique structure of this kind of water allows for electron and proton diffusion through a uniform web of water molecules that are not the traditional H2O arrangement. Instead, they form a lattice. This is the fast transport system that sends out protons and electrons in a wave, so reactions can happen very quickly. When soil is dehydrated, this cannot happen. Organic matter is going to increase nutrient and water holding capacity of the soil, specifically by augmenting clay particles' cation exchange capacity, the CEC. But even further, the hydrophilic nature of soil organic matter, soil life, fungi, and roots make it so together with easy water and the bioelectrical charges and exchanges in the soil, they create structure, communication, trade, charge, exchange, and integration on their own, independent of or less dependent on mineral structures. Explaining how some soils can be pure or nearly all organic matter and still have structure and healthy function. To learn more about easy water, please read Dr. Jared Pollack's book, The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor. Colloids. Colloids are liquids, aerosols, or gels that have substances suspended in them. They can range in viscosity and their constituents. You may have heard of colloidal silver. This is silver particles suspended in water, but colloids are also smoke, fog, mist, blood, milk, gels, toothpaste, emulsions, and foams. Colloids can form crystalline structures or be non-uniform, but they are characterized by not being a solution but containing suspended particles. They are fundamentally involved in innumerable processes key to life, and they rely upon the easy water physics and polarity to do much of their work and to create their various forms. Colloids can trap heavy metals at certain soil organic matter levels in the ideal zone of overlap between EH and pH. Colloids are also a transitionary stage between aggregation of particles, rigid structures, and conglomeration, flexible structures. They are key to forming soil structures in this way. Regenerative Soil begins July 26th. The 16-week course is designed to work for all schedules and to fit into a busy life. If you're interested in a 16-week experience that's in-depth, that teaches you how to work with soil anywhere, regeneratively, with lifetime access to all the materials, resources, and community, now is the time to sign up for Regenerative Soil. Get past the one-size-fits-all thinking in soil science and management. Navigate, understand, and connect the soil biology, chemistry, minerals, plants, all cycles, in all the climates and soil types. Learn how to solve problems and tailor soil to your goals and your plant's needs. Learn how to build, remediate, restore, and regenerate your soil. Learn how to grow pest and disease-resistant plants, and learn how to use a microscope to understand and evaluate your soil. You can grow incredible food, overcome challenging soils, and make the world a better place at the same time. I really hope that you join us. It's going to be fun. It's going to be life-changing. It's going to be groundbreaking and valuable in so many ways. The link is below. I hope that you join us. I hope that you sign up. I'm Matt Powers. Grow abundantly, learn daily, and live regeneratively. And sign up below. Thank you so much for listening.